which is called the intermediate value theorem. So, building off the idea of continuity, if we look at a function like this, I forgot my pointer again. We can see that this function right here of some arbitrary function f is continuous over the closed interval a and b. So what we notice is that because our function is continuous, all right, drawing this curve with a pencil or tracing it out like I'm doing right here, we can see that every y value, okay, between f of a and f of b is covered. And we have some y value outside of here, but that's not going to be our interest. Our interest is to see that every specific y value between f of a and f of b is covered, what we'll call the y value n, okay? So what we can see then is that because our function is continuous, there's always going to be an x value, what we'll call c, on this closed interval a and b that will give that will always give the y value n between f of a and f of b. So all y values will be covered and produced. All y values between f of a and f of b will be produced by some x value c between x equals a and x equals b. This forms the basis for what we call the intermediate value theorem. The intermediate value being our y here, since it's intermediate between f of a and f of b. The intermediate value theorem, we call the IVT for short, states that if a function f is continuous on the closed interval a, b, then for every y value n between f of a and f of b, there is guaranteed to be an x value c, and again the formatting here when I copied these from my notes didn't work out, for c greater than or equal to a or less than or equal to b, such that f of c equals that y value n. Okay? So a way you think about this is what I like to call the guitar string theorem. Specifically that if you have a guitar string between 2 points, let's say a and f of a and b f of b, if you pluck that guitar string, the guitar string will wobble back and forth and sweep out every value between f of a and f of b. So as a result, there's always going to be some point along the guitar string where a guitar string is equal to all y values between f of a and f of b. The other way they like to state this is they call it the pencil theorem. That if you don't lift that if a function is continuous, then when you trace its curve, you're never going to lift your pencil in between f of a and f of b. So as a result, every y value between f of a and f of b will be covered by some x value between x equals a and x equals b. So this theorem, the main use for it is that it can be used to determine whether or not a solution exists over a certain interval. Hence, the intermediate value theorem is what we call an existence theorem. The existence theorem meaning that it helps us determine whether a solution exists prior to actually looking for the solution. In mathematics, for really advanced problems, this right here is very useful because if a problem is very complex, we want to make sure that the problem actually has a solution guaranteed to it prior to embarking on trying to actually find that solution. Because it would be, quite frankly, just a waste of time if we tried finding a solution that didn't exist in the first place. So, applying the intermediate value theorem, the steps that we want to follow is first we want to determine if the function f is continuous over the closed interval of interest, as that is the condition for the intermediate value theorem to apply. Next, we're going to determine the value of the function at the endpoints f of a and f of b. And then lastly, what we're going to do is determine if our value of interest lies between f and a and f of b. If so, a solution is guaranteed. If not, a solution is not guaranteed. A solution could exist, but it's not guaranteed. Okay? So that's why we're not interested in this interval outside of here, because there's no guarantee for outside of this interval of f of a and f of b. It's strictly between f of a and f of b that there's a guarantee with this intermediate value theorem. Again, we must make the function sure the function is continuous, otherwise we can't apply the intermediate value theorem. And then once we know we can apply the intermediate value theorem, we check the value of the function at the endpoints, and then see if our value of interest lies between the function values at those endpoints. So let's look at an existence of a solution with a tabular example. The function f is a continuous function defined over the interval x greater than or equal to 0 and less than or equal to 8. Over this specific interval is it guaranteed that f of x equals 0. So we apply our conditions once again. So the first thing is that the conditions for immediate value theorem are satisfied as f is continuous and the interval is closed. This is how it will appear in tabular examples, such as on the free response section of the exam. It'll say f is a continuous function, so that's the prompt that you need to be looking for. You need to be reading the prompts of the free response section carefully. 2, okay? F of 0 equals 3, and f of 8 equals 3, okay? So that is what we can see from the table right here, okay? So now we move to our third step. What we can see is that our y value of interest, 0, is not between 3 and, well, 3, and I don't know why that m is there. So a solution to f of x equals 0 is not guaranteed on the entire interval, okay? So we can't guarantee a solution to f of x equals 0 in this entire interval. It could be possible, but it's not guaranteed because it does not lie between f of 0 and f of 8. So now let's look at an algebraic example. Is there a solution determined to this equation f of x equals 6 when f of x equals x cubed plus 4x minus 2 on the closed interval 0 to 3? So as we've talked about, since f is a polynomial, it is continuous automatically, and we know that the interval is closed, so the conditions for the intermediate value theorem are automatically met. Next, we evaluate our function values. Okay, so f of 0 equals 0 cubed plus 4, 0 minus 2 gives us negative 2, and f of 3 equals 3 cubed plus 4 times 3 minus 2, which will give you 37. So what we can see here is that 6 does lie between negative 2 and 37, so the intermediate value theorem does guarantee that f of x equals 6 at some point on the closed interval 0 to 3. And this is how we would state it if we were writing a mathematical paper or we're answering a part on the free response section of our exam, okay? And again, my formatting here is just terrible. There's no spaces, and English teachers would have a heart attack. I'm having a heart attack here. So, determining lower bounds on solutions. The lower bound describes the minimum possible number of solutions, and the upper bound denotes the maximum possible number of solutions to an equation, okay? This is interesting for cases where we may not be able to get an exact solution, okay? So, for example, the number of stars in the Milky Way we're not sure about, but we know that there is a lower bound of 400 billion stars, which I just looked up on Google. Totally know that, and totally did not look that up on Google. So we say that the lower bound of the stars in the Milky Way galaxy is 400 billion, which is also, off on a tangent, a exceedingly large number to think about. Can't even think about it. So our steps to do if we want to determine the lower bound of solutions over an interval is we determine the function is continuous over the closed interval a to b. And again, these problems will focus on strictly tabular scenarios, okay? They're not going to focus on algebraic scenarios. The next thing we do is we determine the value of the function at the endpoints of subinterval. The subinterval is little mini intervals that consist of a point and the point most adjacent to it, okay? So 0 and 2 would be our first subinterval, 2 and 4 would be our second subinterval, 4 and 6 would be our third, and 6 and 8 would be our fourth subinterval. Okay, so we start with a point, and then we go to the point adjacent to that, and that gives us our subinterval. And then lastly, we apply the intermediate value theorem to that subinterval. Okay, we determine if the value of n, interest n, lies between the function value at each endpoint of our subinterval. So we'd see if n, for example, for a first subinterval, we would see if n lies between 3 and 7. If so, a solution is guaranteed on that subinterval. If not, a solution is not guaranteed on that subinterval. So let's look at an example here that deals with this table that we have shown here, okay? The function f is a continuous closed function, or a continuous function defined over a closed interval from 0 to 8. Over a specific interval, how many times does f of x equal 4 at minimum? So again, we know that f is continuous over a closed interval, so the conditions for the IVT are satisfied. Now we look at our first subinterval, 0 and 2. We see that f of 0 equals 3 and f of 2 equals 7. So since f of x equals 4 is between 3 and 7, we have a solution guaranteed over a subinterval. So we know we have one solution so far. So now what we can do is we can move on to next subinterval. From 2 to 4, we see that we have y values of 7 and 11. 4 is not between 7 and 11, so we have no solution guaranteed over this subinterval right here. Moving on to 4 and 6, we see that for 11 and 9, 4 is not between 11 and 9, so we have no solution guaranteed to f of x equals 4 over this interval. And then lastly, from 6 to 8, we see that f of 6 is 9 and f of 8 is 3, so f of x equals 4 does lie between 9 and 3, so we do have a solution guaranteed. So we have, at minimum, two solutions between 0 and 2 and 6 of 8, at minimum over the entire interval. And this encapsulates the idea behind the intermediate value theorem.